what I'm going to show now is how the process of dealing with the wavelength of light and what happens to cause the redshift and possibly the peculiar motion of objects. What happens for astronomers, this is. Well, we can say that a proper source of light is located on a position we will call R0. This R0 is where the observer is too. We know that certain elements emit light of certain frequencies and wavelengths, and we can identify what elements are available in or are showing in other galaxies. So it's a good form of reference that light waves are produced near us, and they're consistent with the composition of the matter or the star or whatever. Now, how do we define a light wave coming from a source at R0? Well, we could say one wave goes from here to here in a certain period, t. I'm making that a t, and we could call it a tau, but that period is the time it takes to go from the initial position and one cycle later ending. That means that it moves for a distance consistent with the math of the XBXB universe, R0 e to the H0, which we're all expanding properly with H0, and we'll call that tau. So in H0 tau, the wave is complete, and we could call that first wave lambda 0. Now we're saying that the source is stationary, and this is moving with respect to a stationary universe. Now I say that with the thought that if this light moves on, we have seen that it moves faster than the proper flow, and this represents a wave that was produced by a source that's in the proper flow. So this wave will be moving at the speed of light relative to anyone observing the motion of the wave. Well, the wave continues moving on until it hits a detector. And obviously, I have said the direction of motion of that wave is in that direction. These are just standard things you do. One other thing is that the frequency of the wave is the inverse of what's called, this tau is the period. That's the time it takes to start and finish one wave, and nu is equal to 1 over tau. Now there's a little problem with the standard model in that these equivalencies don't always work out as they should, and this will rectify everything. Now you have a source, you have a location for the wavefront, and we realize that this wave will be moving at the speed of light relative to the flow, which is already moving at the speed of light relative to a stationary universe. We know that, for instance, that for the flow, R0 e to the HO times 0 is R0. For light, R0 e to the 2HO times 0 is 0. Okay, what I'm saying here is that the expansion constant, the exponent has an expansion constant. For proper motion, it is HO. And we've discussed this before. For light, it's 2HO. So when you differentiate, you use these as your constants. And also, proper is the same as peculiar. So the peculiar and the proper motions are both expanding according to peculiar, are expanding according to HO. Expansion is essentially dictated by HO. Now, as this wave moves through space or through a delta t, which we call the time of flight, this is not flying, but it is moving from here to the detector. All that way, it is expanding in size, in length, by e to the h0t during that time. Well, we've defined the from this diagram here, we define the base wavelength. We could call it the base wavelength of that base wavelength is equal to R0 e to the h0 tau minus 1. And all I'm saying here, I want to adjust this a little bit. Okay, all I'm saying here is that I'm subtracting this location from that location and finding out the wavelength. That's the base wavelength. Now, what happens to that wavelength as time goes on? It expands relative to the expansion, the proper expansion. And that's why everything's expanding at that rate. And that's why if we pick up a signal from a distant galaxy, it has a wavelength which has changed dramatically, well, not necessarily dramatically, which has changed from, let's say, hydrogen. Hydrogen wavelength comes in longer, so we use that information to determine that the galaxy we're looking at is a certain distance away. As the wave propagates through space, it increases in length relative to the proper observer. And this is what is observed by him or her at that location, this location here. As it moves, it expands relative to the proper expansion. Now, the flow is, by the way, the proper motion. Okay. Now, the received at the detector, they get lambda prime. Lambda prime is equal to the wavelength at the detector. And you can see it's time dependent. So therefore, this wavelength will be dependent upon how long has that wave been in motion. Wavelength. How long has it been in motion? And the lambda prime is equal to, therefore, it's the base wavelength simply multiplied by e to the h0 delta t, and we will call delta t, I love this, it's time of flight. Now this could be up to, it could be like 14 billion years, or it could be 2 hours, whatever it takes. So the original wavelength times the time of times the expansion factor. This is the expansion constant here. This is the time of flight. E, of course, is your base. The wavelength at the detector will be somewhat greater because e to the h of 0t is a longer wavelength than, of course, lambda 0. This accounts for what we call the redshift of the proper galaxies. Okay, so it's as simple as that, but the math has to be addressed. The redshift of a proper galaxy is a method by which we can determine how far away the galaxy is by using the equation lambda prime is equal to lambda 0 e to the h 0 t, where t is the time of flight. We can say then that lambda prime over lambda 0, just cross multiply, or I should say just a little algebra, is equal to e to the h 0 t. Taking the log of both sides, you find that h 0 time of flight, delta t, this should be delta here, h0 delta t is equal to the log of the other side, which is the log of lambda prime over lambda 0. From that, you come out with delta t, and that is the time that this light is propagating through space between the galaxy and ourselves. Delta t is equal to the log of lambda prime over lambda 0. And just making sure that we've got these definitions down. Lambda prime is that which you receive. Lambda 0 is the rest wavelength of the radiation, and this divided by h0, which we're getting a good feel for recently, h0, that's delta t. Now, knowing delta t, you see, you can calculate that delta t helps us e to the h0 delta t is equal to r, that is the distance to a galaxy. Okay, now I might say that the method they use right now is they use Lorenz's gamma, and we know that gamma is equal to the square root of 1 over 1 minus v squared over c squared. These are zeros in here. That's gamma, and you use that to calculate what velocity, what is the velocity of the galaxy in question. Using the velocity, you can find out the distance according to non-exponential mathematics, which is wrong.